Welcome everyone to part 2 of integer handling. Today we're still going to look at, this time we're going to look at how to convert int into a string so that we can, print it out. And on the right hand side, we have a simple C code. The C code essentially does the Gaussian addition, the Gaussian formula, using the Gaussian formula for the sum of n integers. And then after it simply prints it out. Okay, so over here we write our prompt and the prompt length as usual. Then we write it out to the standard out. Then we read the user's input. We place the user's input into buff, which is already defined here. Then we convert that into an int, the user's input into an int using the function atwa, as we've already seen. Then we do the Gaussian computation. Then we convert the Gaussian value back into a string. Essentially, we are converting it into this output string. We write it out, then we also add a new line character, then we exit gracefully. And so essentially, let me show you guys how this looks like. So I save this, then let me compile this. And of course, we pass in, say, 4. Then we have our solution to be 10. What this means is, for example, if we want to sum the numbers from 1 up to 4, the return value is essentially this. So that is 4 plus 3 plus 2 plus 1, which is 10. And that's exactly what has been outputted. Okay, and the Gaussian formula is as follows. So it is said that the Gauss's teacher says he should sum the numbers from 1 up to 100, and then he came about with a simple formula. So we have s is equal to 1 plus 2 plus 3 plus 4 up to some n. Then Gauss also once again wrote the numbers backwards. So from n backwards up to 1. So n minus 1, n minus 2, n minus 3 up to 1. And it just so happens that if you add these two, well, we add this one and this one, we're going to have 2s. This one and this one, we see that we have n plus 1, this one and this one, n plus 1, this one and this one, n minus 2 plus 3, and so on. And we're going to have it n plus 1 n times, okay? So we have n plus 1 times n, and you divide both sides by 2, then we have this, and it's the same as using a shift to right, 1. 1 because the power of 2 over here is 1. And so that's essentially Gauss's formula. Okay, so let's go back to our C code. So that's essentially what's happening here. We have the Gauss's formula. Then we have our output. We uninitialize output, for which we're going to convert the Gauss's integer into a string. Okay, so in our output, this what happens. Say we reserve 20 bytes, yeah? We reserve 20 bytes for the output, where the bytes, when we try to read the bytes, it's garbage. So I'm using question mark to represent the garbage, and there are 20 of them. And so essentially, how do we convert the integer, which is the Gauss's value, and place them into the output? So we start at the very last end. Okay, at the very last end, we place a null terminator. Then we shift it 1 to the left. Then we convert the Gauss's value into an ASCII character, which is 0, then 5, then 0, then 5. What I mean is this example is for when n is 100. Okay, it is well known that when n is 100, the solution is 50, 50. Okay, so the algorithm is as follows, as we would see in the code over here. So the algorithm is as follows. So we have 50-50, and of course, when we place in the index, we consider the index, this index 0, 1, 2, up to 19. The 19th one is going to take a null terminator. Okay, so that's no brainer. Then we shift the index to the 18th one. And how do we get this particular 0? from the number. Mind you, this is an integer, and then we're trying to convert it back into an ASCII character for the numbers. So on the 18th one, what we're going to do is we're going to take the Gauss's number, then we find the remainder using the modulo operation. The modulo operation tells us that 50, 50, the remainder is 0, okay? And the 0, we're going to add it into the ASCII character of 0. The ASCII character of 0 is 48, and we realize that it's still the same 48, so now it's being converted back into an ASCII character. Then we're going to find the quotient, that is 50 divided by 10, and this gives us 505. Then our index is going to shift from the 18th one to the 17th one. So now our Gauss's value is 50, 50. So we do another remainder again. Then we have, 505 modulo 10, we have 5. Then 5 plus the ASCII character for 48. That is, this what I mean. So 5 plus the ASCII character of 48. When we add 5, we're going to have the ASCII character 45. So we have 53. Then we continue on, and so essentially that's the entire algorithm. So we continue on until our Gauss's value is 0. That means we've already written all the numbers that we need. So we're going to write it backwards. So 0, 5, 0, 5. Okay, so 0, 5, 0, 5. Yes, and after that we're going to offset and then count it from this part up to the end. And then we're going to print it out. So we're going to shift the output address. Usually the output address is going to be the very first one. So we're going to firstly shift it to 19, then subtract up to this one. Then our new output, final output address is going to be this. So whenever we want to print it out to the screen, we're going to start from here until it meets the null terminator. Okay. And so one glaring problem that the more perceptive of you would have noticed is that this algorithm works fine. As we've seen, we've tried it out, but here's a case it cannot actually print out 0. For example, there is no case where the Gauss's value is going to be 0, but let's say we want to make it, say, here the Gauss's value is 0, and then we try to, the definition is fine, yeah? Let me try to compile this and then run it. You see that it prints nothing. That is because the code is essentially going to print this one, the null terminator, of course, and then after it prints the null terminator, we see that it prints a new line character to the screen, and 0. The fact that 0 is not showing is because when Gauss is 0, this while loop does not work, and then it jumps straight from this to this and then this, and so 0 is never really printed out. So for us to include 0, we use a loop called the do while loop. It's actually quite ancient, but sure. I don't know if it's still used in production. So when we use the do while loop, we save it. The do while loop essentially tells us that we do this one once before we begin the condition while loop, then we continue on again and again and again. So this executes once first, then we do the while loop again and again and again. Okay, so let's compile this, then let's write this out, and then we see that now our 0 has been printed. Okay, so we ought to use the do while loop. Let me open the C code, and then let me do this. Yep. Okay, so now we're going to look at the Nasm code of it. So on the right hand side, well, it follows our usual way where we have these ones are already initialized, so it goes under our .data section, which is the prompt and the prompt length. Then we also see that our very first thing we do is we print it out to the standard out, and so that is here. So we print it, and we write the prompt to the standard out. Then what next? Over here we do, this is uninitialized, this buff is uninitialized, so the buff goes in here, okay? And then next thing we do is we take from the user the input. So we read the input from the user, and then that is here. We've already seen this. Then we convert the user's inputs to the user's input, which is now placed into buff. Okay, the user's input is now placed into buff, same over here, placed into buff here, and we convert it to an int using the function atwa, which you've already seen in our immediate previous like video. And then I place it into a variable called tunum, and tunum is already reserved over here as a quad word, which is 64-bit integer size. And then we're going to do some computation, but before that, I use the RCX for the gauss, and then after the entire computation, I place it back in here. Okay, so essentially what happens is here I initialize the RCX to 0, and then we begin the computation. So I place in back the tunum, which has already been converted into the RCX. Okay, so that is just the spot. Then I place in the RCX again into R9, and then I increase R9. If I increase R9, now it's going to be the tunum plus 1. Okay, then R9, so it's essentially R9 is this whole part, the tunum plus 1. Then I'm going to multiply the RCX by R9 because now the RCX is tunum. Okay, so RCX times the R9. So essentially we have all of this. Then after multiplying here, then we're going to do a shift right, which is a division by 2. Okay, so it's pointing right, so it's a shift right. And the power of 2 over here is 1, so we do a shift right. Then after I'm placing the variable, the value in RCX back into our gauss. Okay, our gauss is also initialized up here. Yep. Okay, and so after this, we essentially going to have to convert it back to a string. Okay, so this is uninitialized, right? This is uninitialized, so that goes into our BSS section. Over here, we reserve 20 bytes for writing it back out to the standard out. Then, firstly, we initialize int end, where end is essentially the index 19, as we've already seen. So output end is going to take the null terminator. So essentially, because we're going to do some divisions by 10, I'm now using RCX to hold a 10. Then RBX is now holding the output, the address of the output. That is to say that RCX is now, the address of the output where it starts from this particular one. And so our very next step is to add 19 to it. That means we shift in for this address. We know, say if the address is, say, OX, I don't know, something 00, then we are adding 19 to it. Okay, so let's say this particular address is this, then we add a 19 to it. Okay, that's 00 plus 19. When we add 19 to it, it's essentially going to become this. And so it shifts from this one to the very last end. And then we have the address for the null terminator. Okay, so RBX is an address. And RBX is an address, so we're going to place in, we add 19, shift it offsets. Then we're going to place in the null terminator, and null terminator is essentially 0 in ASCII. So we're placing 0 into this. Okay, essentially because RBX in itself is an address, we have to dereference it. That's why we have the square brackets. So the 0 goes into the RBX. Then essentially I'm going to place the Gauss value into the RAX, because the Gauss is of type keyword. Okay, we're going to place it into the RAX. Now we enter into our do while loop. Okay, in our do while loop, we see that the end has been subtracted. It's been decremented. So we use the dec operation, which means decrements the end. Okay, so essentially RBS is still an address. So we know this address now, which is 19. We're going to decrement it, and then we're going to have, say, 18. So now it's pointing to the side. Okay, and when we decrement it, we're going to clear a remainder. We're going to prep the RDX. Why are we prepping the RDX? Because we're going to do a division next. Okay, what do I mean by a division? So essentially our Gauss value in itself, okay, is placed into the RAX. And whenever I want to do a division, use a division, essentially we're going to have our numerator to be the RAX divided by our RCX. Okay, so supposing this were R9, then R9 is going to be our denominator. It's always going to be RAX divided by the register you place in here. Okay, so essentially I told you RCX now contains 10, okay, which is this one. So we're doing a division. When we're doing the division, we have this one to be 10, and then our RAX, which is our Gauss's value. And then after the division, our quotient for the division is going to be placed into the RAX, and our remainder is going to be placed into the RDX, okay? And our remainder is essentially what we need, because this operation is a remainder, or a modulo operator, which essentially is a remainder. Then after, our remainder is going to be placed into the RDX. So essentially our value in the RDX is going to be added to the ASCII character for ASCII number 40, okay, which is 48. Yes, which is 48. So essentially we add the RDX register to the ASCII character for 0. Okay, and why am I using DL? Okay, essentially using DL. DL is a part of the RDX register which contains the remainder. What do I mean by that? So essentially registers look in this form. Okay, so let's say the entire register is the RDX, which is the 64 bits. Okay, half of it is going to be the EDX, okay, which is 32. Then half of the half is going to be the DX register, and then the smaller part, which is the 8 bits, is going to be that for the DL. Okay, it's saying, we can see that over here. So for the RDX and the EDX and then the DX and then the DH or DL. Okay, and so for other registers also, we have the RAX, EAX, AX, AH, AL. We just want to use the lower parts of the registers. Okay, so RDX contains the remainder. We add the ASCII character for 0, and then we have, so essentially now we have all of this. So we need to place all of this back into the output end, and the output end is essentially the RBX. Okay, so that's the address. RBX is the address, so we're going to dereference it and then place in the DL. Okay, so we're placing it into the value of the address. Okay, then we test if the quotient of the remainder is 0. Then we jump if it's not 0 to the next digit, so it's going to begin the loop again. It's going to continue on and on and on. So essentially we've done all of this. Okay, and after, we're going to write to the standard out, and we already know that for writing, 1 goes into the RAX, 1 goes into the RDI. This time around, the output, or the address where it starts from. So if we want to say, let me show this. If we want to say, so now the output begins from here, so we need to use that offset. Okay, so that's why we're using the RBX for that. And then RDX usually contains the length, but this time around the length is not just 20, we also need to offset. What do I mean by offset? So we know the entire length to be 20, and then so we're doing 20 minus the value, the index over here. So 20 minus the index over here, so that we know the number of bytes that we need to print out. Okay, and so we have moved the output to the RDX. Then we add 20, so it goes to the very end, and then we subtract to, it's going to one more than the size of the output. Then we subtract the RDX, and then we have the offset. So it's essentially this. So 20 minus the end. Then we do SS call. Then after we print a new line, just as over here, and then we exit successfully. Okay, so let me try running this code to show you guys how it works. So I save it. So I'll run.sh gg. I called it gg. So when I try to run this, so 4 should be 10. So we have a segmentation fault. Let's analyze it. So we're going to use GDB to analyze it. So we run this program. We run this program, we place in 4. Then we see that it's giving us an error once more. So let me open our code over here, gg.asm. Okay, so back to the GDB, we see that we have a segmentation fault. So we do BT, which is the backtrace. We need to find where the segmentation fault occurred. Then we read the error, but we see that over here it says something about Atua, and then the fact that in the underscore starts in gg.asm line 37. So let's look at line 37. 37 is this, so it should be around this area, or at least up above here. This one looks fine. We're writing it out. This one also is the user's input. So over here is the problem, because we don't need to pass in the return value for the resys score, but rather we need to pass in the buff, because Atua takes in the buff instead. Okay, so we save this. Let me exit here. Let me just exit here. Then let me try to compile it again. Then GG, we enter 4. Then we have our solution to be 10.